Okay, so I didn't want to force you guys to listen to me do the dirty details of writing up this problem. So we're going to do another Hooke's Laws problem. Suppose that 5 joules, so that's a 5, not s, 5 joules of work is required to stretch a spring from its natural length of 20 centimeters to 30 centimeters. All right? I want to know how much work for 20 centimeters to 25 centimeters. Okay? Now, you got to be really careful. You got to pay attention to your units, because if you're not careful, you'll screw this up. Notice, that's a unit of work, isn't it? Now, remember, regardless, when we talk about Hooke's law, we're talking about, remember, F, the amount of force required to hold a spring that's been stretched at a certain distance. To hold it there is K times X, right? But this gives me work. And I'm unable to solve anything unless I know what K is. So my first job is to figure out what K is. So all I'm going to do, I remember from the last problem, remember that work is just the integral from some value A to another value B of Kx dx. Remember, dx was the distance that you're actually stretching it through each one of those distances, all right, from our delta x. So the first thing that I need to do is solve for what K is. Well, I've got a unit of work right here. So I can say 5 equals the integral. Now, what are my, I've got a natural length of 20 centimeters, and I'm stretching it to 30 centimeters. Now, a common error that students make, there's all kinds of pitfalls in this problem, so you got to be real careful. Common error that students make is they go, oh, that's easy, it's from point 2 to point 3. No, it's not, because the length of the spring prior to being stretched is 20 centimeters. It's not being stretched at all. It requires no work to stretch it 20 centimeters because it's just sitting there at 20 centimeters. So we're really going from 0 to 0.1, right? We're going 10 centimeters. I'm stretching it 10 centimeters of Kx dx. Now you may say, okay, wait, how am I going to solve for K? Well, it's easy. Remember, K is just a constant. So I know that 5 is equal to, I'm going to turn this into a script K, Kx squared halves from 0 to 0.1, right? Doesn't this imply that 5 equals, let's see, now 0.1 is a tenth, so 0.1 squared is 1/100th, so this turns into K over 200 because of this little half here, right here, right? So K equals 1,000. Now we have our spring constant. Now, all I'm trying to do is figure out how much work it takes to stretch it from 20 centimeters, its natural length, to 25 centimeters, right? That's 5 centimeters further. So I know, or farther, I did it again. So I know that the work required is the integral from its natural length, no stretching required, which is 0, right, to 0.05. Now, if I were going from, say, 25 to 30, then I'd have to go from 0.05 to 0.1, right? Got to be real careful about that. You just got to, like I said, there's a lot of pitfalls in this problem, of 1,000 times x dx. And this guy ends up being, what is that, 500x squared, right? Because it's 1,000x squared over 2, so the 2 goes into 1,500 times from 0 to 0.05. So this guy ends up being 500 times 0.05 squared joules when everything's said and done. Now, think about this. If it takes 5 joules of work to stretch it 10 centimeters, how much work is it going to take me to stretch it, excuse me, 5 centimeters? Now, some of you may say half, but as you're about to see, well, let's see. Watch what happens. I'm going to grab my calculator here real quick. Move you out of the way. Where's my calculator? There's my calculator. So I'm going to go 500 times 0.05 squared. And I'm going to hit enter, and I get 1.25. So this, wow, that's strange. That's the same as the problem from before, isn't it? 1.25 joules. It took a fourth of the work to stretch it to 5 centimeters. So, and it makes sense, right? The more you stretch a spring, the harder it's pulling against you, especially a really stiff spring. Okay? All right, that's a fun one. Now, we're going to change gears here a little bit. All right, so I'm going to push pause again so that you guys don't have to go through all the gory details with me about writing up these problems. And I'll meet you back here in just a sec, okay? All right, now this is a really good problem. This is a lifting problem. So check this out. I've got a 100-meter rope that weighs 10 kilograms. If it's dangling from the edge of a tall building, so what I got is a tall building right here, right? and this guy is dangling from its end. I suppose I should have said that. And let's say that this right here is 100 meters. It's a long rope. How much work is required to haul the entire thing in? Okay, now I'm going to show you the way that I do this. Some of you may have experience with physics. You may have a different way, which is fine as long as you walk me through it and you make sure that you do the calculus cleanly. Now, watch this. Here's what I'm going to do. I'm looking for work, and I know that work equals force times distance. So here's what I'm going to do is I'm going to haul a little bit of this rope in. Okay, I'm going to change colors, and I'm going to haul the rope in. So let's say that the rope is right here, okay? And I've hauled the rest onto the building. It doesn't require any work right there, all right? So there's my rope just a dangling, okay? Now, I'm thinking of this from the bottom up because in my brain, that's the way that it makes sense. I'm going to let that distance be x sub I. Remember, that thing's changing as I haul this rope entirely in. Now, you may already be going, okay, if that's x sub I, then that right there is 100 minus x sub I, right? Okay, so let's play with this just a little bit. What I want to think about is not just force times distance, but mass times acceleration times distance, right? That's kind of an interesting way to think about it. Now let's do the mass. We're going to build this thing one chunk at a time. Let's do the mass of the system for when I've raised this thing x sub I. So this is the mass of the ith system, if you think about it. Well, what is the mass? Well, the mass of the rope is 10 kilograms per meter, right? So if I go, or excuse me, 10 kilograms per 100 meters. So I've got 10 kilograms per 100 meters, right? But there's only one problem. That's not a mass. That's a mass per unit of meter. So let's think about that. What I need is I need a distance that's going to cancel out this meter. So if I look at this thing, right? What do I have? Well, I have a little sliver of action, don't I? I have that little sliver. If this is x sub I, then there's this little sliver right here, which I'm going to call delta x. And the units on delta x are in meters, because x has units of meters, and 100 minus x has units of meters, right? So I know that the mass of the system is going to be 10 kilograms divided by 100 meters times, now I'm going to put this delta x out here, and I'm going to show that my meters cancel, right? Now, that takes care of the mass of the system when I've hauled this thing up x sub I, right? Now, we know that the force of the system is going to be the mass times 9.8 meters per second squared, right? So this is going to be 9.8 times 0.1, right? Because this is kilograms per meter, times delta x. True? So the work done on the ith portion of the system, the work that it takes me to haul this little sliver right here all the way up, is going to be what? Well, it's the force, which is now I'm getting a little bit crazy, 0.98, because 9.8 times 0.1 is 0.98, times, now what distance am I hauling that? That's easy. That's 100 minus x sub I, right? Times delta x. I'm just using the commutative property of multiplication to move that thing around where I want to. This guy and this guy make up the force. This guy makes up the distance. So the total work that I have to do to haul this thing up, well, where does x go from and to? Where am I hauling this from? If I start at the bottom and I think about moving all these pieces all the way up, well, the overall work is going to be what? It's going to be the integral, because I'm adding up an infinite number of infinitely thin little slivers right here. I'm going from 0 to 100 because that's how long the rope is, right? And then I go 0.98 times 100 minus x. Remember, x sub i's turn into x's when they go into integrals, times delta x turns into dx's. So this equals I'm going to give myself a little bit more room on the left. This equals, if you please, the integral from 0 to 100 of 98 minus 0.98x dx, which is equal to 98x minus 0.49x squared, right? Because 0.98x squared over 2 turns into 0.49x squared, and this is evaluated from 0 to 100. So let's see how many joules I get. Well, 98 times 100 is going to be 9800, right? Minus 0.49 times 10,000. Can you do that one in your head? 0.49 times 10,000 is what, 4,900? So 4,900, and then I just get a minus 0, and I end up with 4,900 joules of energy. Now, don't take my word for it. Let's throw this thing in our calculator really quickly, okay? So I'm going to go math. I'm going to go cruise up here real quick to FNINT to make sure I didn't screw it up. I'm going from 0 to 100. I'm taking, what did we say? It was 98x minus, what is it, 0.98x? No, not 98. What are you doing, Ripley? Sorry. Delete. Cruise over here. Minus 0.98x. And this is going to be dx. I'm going to hit enter because I always want to check my work, and look at that, 4,900 joules. Got to be careful though. You notice what I did? I checked all my units. I got kilograms per meter, so I'm good there. I don't have to do any translating with that. And then I just plugged and chugged. But I built this work out one piece at a time. What's the What's the mass of the system? What's the force of the system? What's the work done on the system? It's a really cool way to understand what you're doing in these types of problems. All right, I hope that was helpful. You're going to do a lot more of those types of problems, so I just wanted to make sure that you've seen those, and I'll see you in the next set of problems. Have a good day. Well, not have a good day.